integrity concepts and application.
It's just a workaround.
I didn't take that from my laptop. Maybe
I don't have the cable.
his locals and the backside power just to begin with.
Yeah.
And he has a good talk on the 3D-IC too. So I'd like to go through some of the power integrity concepts and what we do for power sign-off, and give you some kind of ideas and some kind of futuristic research topics on how we can do it for physical design, how we can use these concepts in making the chips better. I think it's kind of like evident that we have the power integrity as a first-class problem in 2D, 3DIC, in this AI world that we are living in. We have billions of instances, billions of nodes in the power delivery network to analyze. We now have HBMs who have like 16 stacks of devices and all that. And it's kind of like a constant problem. It's almost like 20, 25 years old problem, but it's getting worse every day. We improve the design and we make things faster. So what I did was kind of like a typical college student or maybe high school student about this topic. What does the power integrity problem happening? What would it cause us? So even a simple Reddit search that it creates time violations, it makes the chip non-function, it creates functional errors. So it actually puts a lot of stress on the nice design that you might have if you don't have the power delivered to your devices properly. So what's the state of art in the power delivery and power sign-off is we have a couple tools, and our tool is called Emrah Acar. So this has been going through a decade long of innovations. First we started with static analysis and dynamic analysis, much more analysis. But typically what we do is we analyze IR drop into transistor gates. What the gates are typically seeing, the voltage and ground, and based on those, the performance of the gates will differ, the timing will be different. The typical flows are, if you know what the gates are doing, we have a vector flow, which means you actually assign some activity on these gates. This comes down through FSDB or DCD type of formats, or if you don't have any idea, or if you have an early design, and if you really want to try out all possible things, we have vectors flow, which we speculate and generate input factors. So these input factors could honor the power budget, but they also activate the chip in a reasonable, accurate way. You still stress the power delivery network and analyze it. Typically, this takes so many cycles to analyze the entire chip so that you get a good coverage. So we have many different sizes of designs, small to large, with the ICs. Our tools can basically, and our competitors' tools is very good too, they can scale up to many, many cores. So the problem size is bigger, as you might imagine. Like if you're solving a system of billions of nodes, you probably hardly solve in one system. You need to distribute the problem using the solver techniques. But we have good linear scaling as we go with much more CPUs. Our customers are able to run their products on thousands of chips, thousands of CPUs, sorry. But it's still taking too long because it's simulation oriented. So you still need to know a lot about your design. You need to push simulation and analyze the results. So almost 2 decades ago, what we did was we created a static approach where you had a design and you had an average power consumption idea of your design. So the goal is let's analyze the average concept in a DC or static way, where you represent kind of like a static problem or IR problem where your currents are DC currents. You still have a very big power delivery network to analyze, consisting of resistors and capacitors and inductors it can be, and you solve it, and you get some rough idea about the average voltage turn. So it enabled a lot of solutions. I think a lot of use happened, but it wasn't good enough because when you do static, you may miss dynamic behavior, you may miss peaks, you may miss the transient effects. So that amounted to let's solve it in a transient way or a dynamic way, which required to generate vectors, input excitations. From those, we need to know the currents switching on the gates. So overall, dynamic logic was good, but the problem was if you have kind of like a different vectors, you find different hotspots. On the bottom side, you see two blue hotspot map in which they are real, but they happen to be in two different vectors or two different simulations. So it's not easy to find to have a good coverage. To really stress our design in a meaningful way, you need to have a lot of vectors, a lot of CPUs needs to run to make sure that you have the good coverage, you make sure that everything on the design works. So what's also interesting was when you, in more recent technologies, when the gates are switching, they're creating their own self-clocks, meaning that they are actually stressing the most out of their power unit. But more and more what we saw was the drop that we see from the simulation results is not just the cell, it's also some aggressive currents or aggressions from the neighborhood, which means the neighbors are creating much more stress on the victim cells we call, or the instances that's switching, which needed to look into a little different mindset to look at. So simulation is kind of like an engineering approach that a lot of people use, and we still have in practice, but it's not, I think, good enough. So one problem of the simulation is, let's say we have a very simple section of the design. On the left is the red box. This is a cell, inverter cell. On the right, there is a neighbor. So when they both switch, they're going to be coming from the power rail, maybe ground rail. They're going to be utilizing the same resources. So in a way, they're going to affect each other. And you can create a case that they switch together that's going to create a peak aligned mode, which is going to stress the design much more. Or they may be shifted a little bit. Or even they may be shifted to the other side. So all three possible vector generation within a clock cycle can happen. But to really cover the case, you really need to know much more of that. Because you need to, maybe if you want to run dynamic simulation on all the possible these alignment issues, you're going to get zillions of cycles. So in fact, like this, for example, heat map shows the delta on the percentage size, how much of IR drop that you see differently when you create jitters or switching alignment issues. So you may end up getting 10%, 20% different results by just having the two neighbors switching at a different jitter. So that's even worse when you have more aggressives, or you have a one victim on the left, which is again the inverter, and you may have three things. The alignment is really a big problem. So, because it's really, you don't really know when they're doing it, switching. It's exactly, the timing of that is not that easy. They may be switching within their timing windows based on the timing engine that tells us. So it is basically a very impossible problem to cover everything, every instance on the design. So we have a kind of like a good solution for every engineer like Spice, when we have been using it for like a hammer on everything. So basically we have been using transit simulation on many of the power integrated sign-off because it gives us a realistic good result. It's trusted. The models that we feed in is validated. We also have some silicon backup too, but runtime is too high. And you really need to have a little small time steps, and you really need to have very large number of cycles. So that's very prohibitive. So that's why this is kind of done in the late stages in the game, but we wanted to do it as early as possible. If it was a cheap process, we could do early designs and put power integrity concept and analysis much better. So as I said, there's other things that transient analysis is good too. Let's say if you have a package, if you have a chip model, if you really want to have the full design, things are all good. And also if you want to have maybe reducer model creation, you can actually use your transient results to create multiple things too. But I think we kind of have a neat thinking. We needed to have thinking. That's what I think we started almost like 5 years back. New concept called signal DVD. So this is our Ansys' new innovation, which is kind of like a different thinking about the problem of IR drop and power integrity. So by doing this, I'm going to explain a little bit. We have much more coverage, almost like 100% coverage. We can stress any victim instance, the instance that we wanted to care, under very different considerations of their aggression around the neighborhood. And we kind of have a kind of good understanding of where this IR drop coming from. Can we decompose it into multiple pieces? Can we find explainable error? Can we make sure that it could be used in ECO or physical design or other applications? So we have a little bit of an aggressive focus mindset where we are decomposing this IR drop problem into a much more foundational basis so that we could apply to many things like ECO, STA, and a bunch of other things too. And I'd like to give you a little bit of thought so that you could maybe take it and then make it a research in physical design to get better layouts, to get better routing, and all that. So I think this would be very important to do. So, very basic, you have a design, right? You have a sea of gates. This power delivery network is right now coming from the top, not from the bottom. It may come later. But in general, we have a very dense layout. And if you can think of, you have a victim instance that you care, maybe an inverter, maybe a critical pattern or something. It is switching, it creates an activity, it's sucking current from the power rail, but it's also being aggressed by the instances nearby. So if it's switching, it's going to create a power drop. But if the aggressor is nearby that's electrically close to it, switching they also do. So our job is trying to find a limit to what this victim instance is going to see as a voltage. Basically, it's going to like a 10% drop, 5% drop, because it matters in timing, it matters in performance, it matters in thermal, and everything. So the electrical model is kind of simple. We have a very big RC mesh, sometimes L for the high level. But if, on the left side, for example, if your left side is victim and right side is aggressor, the victim is switching and aggressor switching at the same time. It may create a drop on the VDD rail, which will affect its timing. So that's kind of the model that we have. So take into account that we have kind of like a big RC meshes or resistive meshes to simplify. So as I said, I think if the victim is the switch, it may only create a little bit of drop, or we thought it's actually the biggest drop. But if you make all the aggressors around it, as the chart that I showed you, you may really create almost 10 times of more drops. Because now the designs are so much well supplied, meaning that they don't want to have any IR issues, they are actually sometimes over-designing the power network, which is creating a little bit of an aggressive problem more of the time. So in a way that the real thing is when you make all the aggressor switch exactly at the same time as the victim instance, which means you have 9 gates switching poles at the same time, you may get an order of magnitude drop. But is it likely? Was it possible? It's certainly probable, but I don't know the probability of it. So we need to know kind of like a statistical concept to how much probability there is to make them all happen at the same time. So you may avoid it by some delay shifting and all that too, but there's some kind of intuition from the designer and the methodology that needs to come up. So that's what we wanted to decompose the voltage drop. So how did we do that? We looked at the basics. Basically, what's the voltage drop is an I times R. I is the gate current, so we can decompose that. It's a given thing, but we can decompose the R component. So, and R is coming from the self-term, meaning the victim itself, where we have a concept called effective resistance type of thing, when that's the resistance seen by the gate all the way from the supply. And you can compute that. This is basically a DC solve or simple analysis. But there is also another term called PG impact or cross resistance, where you may have a different aggressive point that's creating a current demand, which is creating an instance drop. So in fact, on the middle chart, it's kind of funny that you see kind of like a conic shape. That conic shape is showing the impact of an aggressive current, creating a voltage drop, and it decays down as the distance goes, which means it's creating a kind of like a decaying PG impact around the neighbors, but it is there. And on the top, it's kind of like a layout image, which the red zone is kind of like an eye of Sauron shape, is the most highest PG impact numbers for the aggressor that's shown in the yellow marker. So in fact, this shows this area is very much highly resistive based on the aggressive current in the center, but the cross resistance decays down as things go and the blue is almost like a very minor, very small, negligible amount. But it kind of shows you can create analytics if you have the resistances, then you can export them, or you can understand and create voltage impacts off of them by using simple electrical remodeling of I.R. And you need to think about, are they going to be switching in time together? Are they going to be switching in logic behavior? Maybe things are going to be switching in the opposite direction, or one hot condition, or not. So there's going to be a lot of possibility, but at least we could isolate this to a gate behavior so that we can scalably understand a lot of things. So on the sigma DVD concepts, basically, that I'd like to bring it to you was, these are the concepts that we use in this generation power integrity design, which is IR drop due to self, which is the effective resistance, PG impact, the term that we'd like to use instead of transitive resistance aggression part. And if you know that part, if you analyze all these, you can explain the drop on, let's say, victim U2 based on the current on U1, which is the aggressor. If you know the PG impact term, you can actually isolate what's the aggressor drop versus the self drop. Then you need to apply some kind of risk modeling. Can they switch? Are they going to switch together? Are they mutually exclusive and all that? So if you know the likelihood, you can end up getting some statistical models or some kind of worst case conditions. And from that, you could bound the DVD metrics or the IR metrics based on for each victim. So you have a lot of analytic power once you have all these quantities available to you. So how do we use that? So basically, what I'm saying is to break down an IR metric into multiple factors. So if you know how to compute, if you can actually get to that, you may probably use it on the ECO problem. For example, in this, I think ECO framework that we actually have in play with our partners, we provide the analytics for the ECO engine. So ECO engine, let's say I want to fix a design, fix an IR problem, or fix a timing problem, make something better. I want to move a design, or I want to resize a gate. These things are changing maybe the current profiles, but based on the knowledge and analytics that we have from the power network, we can say that's going to be the delta voltage drop that's going to be the impact is going to be a quantified number, so we give them the information so that they can make a rightful decision whether to commit that change or not. You can also give these aggressors are critical for that victim, so if you really want to have an IR drop reduction on the victim, you can downsize the aggressors too, or move them away, or spread them out. So this incremental computation enables ECU agent to take better actions and much more optimized designs. So on another application, what we have is, let's say this design had a 4x4 identical gates, and this basically has, if you do the IR analysis, you see a lot of like different variability, different hotspots. So where do they come from? So if your design is almost the same, you should almost see the same heat map. But if you decompose all that and look at it, maybe there is something non-local that is explaining all these hotspots. On the top, for example, it happened to be the local issues wasn't creating the hotspots. It was mostly for higher metal layer variability or bump locations. So you get a lot of deciphering from the regional understanding of the IR curve. So if you know that, you can actually understand aggressors. You can find the metrics that you have. If you see a lot of aggression or possible aggressions around blocks, you can spread them out by using different PNR rules. So you can apply in the placement multiple directives that is driven from the PG impact analysis or power delivery analysis, so you can derive them to create spread out designs. Yeah, in fact, I have a picture, I think. On this one, for example, we have some hotspots shown on the left, and they are mostly due to the aggressors nearby. All these high current drawing cells would be like in latches or MDFs. So if you spread them out a little bit, but this IR information, IR analysis will give you that. If you spread them out, the hotspots will go away. In fact, we would highly reduce the amount by applying simple spreading rules. So there's another application that you could incrementally change the simulation results. But I'm not getting to that. In fact, I really want to have this opportunity to give this concept to the physical design research environment so that maybe if you utilize these and leverage all that, you'll do better in the 3DIC or HPM or new applications. And there's going to be a lot of, I think, innovation coming up on that one. So certainly, this is a topic that is important to us, but we'd like to help you as much as we can to create your future research topics. So with that, thank you.
So unfortunately, we don't have time for questions. I was just going to ask, exactly what you said at the end. We really need information to give feedback to this community to actually build maybe a rule-based system that would solve that. At least we need to know what design rules to check. All right, that concludes the session. We'll have a break coming up. Thank you very much.